So I've been playing around with one of these DC rectifier modules to get regulated DC out of my Variac, basically, to do some higher voltage electrolysis experiments with. And I realized that because when I would load this down enough, there was quite a bit of ripple happening. So I'm going to swap out this capacitor to see if I can improve the ripple, and in the meantime I figured I would make a quick video about what this ripple even is and how you can measure it using a regular oscilloscope with two probes. So what I have on the scope here is two waveforms, the yellow and blue. Yellow's channel 1, blue's channel 2. Channel 1 is probing the positive outlet of the DC rectifier, and channel 2 is probing the negative. And channel 2 is inverted because the negative side obviously goes negative with the DC voltage. But when you add these two waveforms, you get your actual output waveform of what it looks like from the rectifier. And if I start turning up my voltage here using the Variac, you can see these two waveforms are getting bigger as I turn up the voltage, and they're adding up to the steady DC output. Now this is unloaded. This is just into an open circuit essentially. It's slightly loaded by the probes, but not very much at all. And so you can see that we have a pretty good low ripple DC output here. Let's see if I measure. It's saying peak to peak on my math wave, which is this red guy. I'm somewhere between 2.4 and 4 volts maybe. So it's, you know, it's very low relative to, you know, currently I'm at 96 volts, 95 volts out. So it's within 5% of the voltage is the ripple. And the way these modules work is you give it, you know, whatever AC voltage you want up to a set maximum. I think this module maxes out at like 320 or something. So the AC goes on this side, and then your DC out comes out here, and it's based on the AC voltage that you feed it. And here's the full bridge rectifier, just 4 diodes, along with the capacitor, which charges up during the increase of the wave, and then it discharges when you're loading the circuit and the wave is at a, you know, when the wave isn't at its maximum. So this helps you reduce the ripple, and if you increase the capacitance of this capacitor, then you even out that ripple more and more. And I'll show what it looks like when you start loading the circuit, because that ripple becomes pretty obvious. So here's what it looks like if I actually have some kind of load on the circuit. So we're up to 23 volts, and you can see how much the red is dropping down basically. And if we take it up even farther, you can really see how bad this drop is. I mean, it's saying 36-ish volts peak to peak, which is quite bad. It gets slightly better at higher voltages. So if I take it up to about 65 volts, now it's 14 volts peak to peak, but you can see that ripple drop as the capacitor is struggling to keep up. So it's dumping energy, then it needs to get charged. And it just doesn't have quite enough energy to keep it nice and steady across here. So the idea is to take the capacitor and replace it with a bigger one. So this is the capacitor that I'm going to replace it with. Same voltage rating, 450 volts. But it's 1000 microfarad instead of 220. So here's the finished setup with the old capacitor desoldered, and here's the new capacitor, and I just soldered a couple of lines in its place here. Maybe I can show it a little better. There we go. And then I just have these connectors, so I can connect essentially as many as I want. Currently up to 2 capacitors in series. So I'll show kind of what the ripple looks like with one of these 1000 microfarad capacitors, and then 2 of them. Oh, I said in series, I meant in parallel. Definitely in parallel to increase capacitance. Here's the waveform at 18 volts, and we have about a 5.6 volt ripple at 18 volts. And keep in mind that with this setup, because this is an electrolysis setup, the lower voltage up to a point, there's a certain pinch point voltage, as they call it in literature, or at least in a couple of papers, around 40 volts for this setup, where up until that 40 volts your load is steadily increasing, so you're drawing more amperage, you're loading the power supply down. And then after 40 volts you get this pinch point effect, and the amperage that can pass through the circuit drops significantly because your circuit resistance goes up. And so up to that 40 volts is where you would see the worst ripple from a power supply like this, because it's being loaded down. And then after 40 volts your ripple should decrease, and should be able to show that. So we're increasing right now 20 volts, our ripple is about 6 to 7 volts. Now we're going up to 28, 30 volts. Our ripple is up to 9.6 volts because we're loading the circuit down. Now we're at 40, and you see how the ripple kind of went away. So ripple is back, and then as soon as we get to 40, it evens out because the resistance of the circuit has dropped, and now the ripple is roughly 4 volts. And it's gonna stay around there. Now it's gonna increase a little bit, but basically once you're past that pinch point, you're in this area of where the circuit resistance for the electrolysis cell is much higher, so you can't load down the power supply as much. And now I'm gonna put the second capacitor that I have in parallel with this other one, and see what kind of, we should get even a better, less ripple than we did with just one capacitor. So here I have both capacitors in parallel, hooked up now to the rectifier module. With one capacitor we were looking at roughly a 4 volt ripple. So let's see what we get now. So now, wow, 5.6 at 20 volt. Yeah, it's already looking better. 6.4 at 30. There's our 40 volt cutoff. Now we're at 3.2 volts. 3.24. Okay. So I'm not sure if it is picking up much of a difference at this point. It might also be that I'm not measuring it. I'm not quite able to catch over here the difference in this red waveform with the scope. But either way, it is much better than it was with that small 220 microfarad capacitor. I'm going to try and zoom in on that math one a little bit. See if we can get a little more resolution. 10 volts. Yeah. So you can see it a bit better. And if we go to the measurements, we got 4.8 volts peak to peak at 36 volts. Now it's going to even out slightly. Got about 4 volts peak to peak. Yeah, the power supply works pretty well. Now, if you're gonna do this type of thing with these capacitors, something to keep in mind is that these things are pretty beefy, so they're actually gonna store a good amount of energy. So this is charged up to about 24 volts. If I now discharge it, see that's quite a bit there. So definitely be mindful of that if you're going to be doing this kind of thing with power supply. You know, these capacitors, if you start putting a bunch in parallel, you know, these are 450 volts, 1000 microfarad per. The energy stored starts shooting up, and these things can get kind of dangerous. But yeah, this worked pretty well. This little module just came from Amazon, pre-built. It's like 20 bucks or something. It worked pretty well. They've got some, I think some high frequency filter stuff. I'm not totally sure what the rest of the circuit on this looks like, but I think that there is some essentially LC filtration happening on the AC input side, but and then there's also a 10 amp fuse here, but the general function of this capacitor, or sorry, the general function of this module is it takes AC in, it rectifies it full bridge, so you get both sides of the wave, of the AC wave, rectified to DC, and then you use the capacitor to even it out, so that way you get a nice flat DC output rather than a ripply one.